In the world of modern manufacturing, it's all about one thing, really: speed. How do you make parts faster, more efficiently, and just stay ahead of the curve? Well, the answer lies in mastering a single, absolutely critical concept. And here it is. This is the fundamental challenge, right? It's this constant tightrope walk between speed and precision. If you go too fast, you might ruin the part, or even worse, destroy your super expensive equipment. But if you go too slow, you're just losing productivity, and let's be honest, you're losing money. So how in the world do you find that perfect balance?
Well, the answer starts right here, with understanding this one metric: material removal rate, or MRR for short. The easiest way to think about it, it's kind of like a printer's pages per minute rating, but for carving metal. It's just a pure measure of productivity. How much stuff can you cut away in a certain amount of time? The higher your MRR, the faster you're making your part. Simple as that.
So in this explainer, we're going to unpack exactly how to crank that rate up. We'll kick things off with the smartest strategies, the ones that don't cost a dime. Then we'll dive into the advanced physics that are literally redefining speed, explore the incredible tools making it all happen, and finally show you how to tie it all together.
All right, first up, it's not just about pushing the machine harder, it's about working smarter. You'd be amazed, but some of the biggest gains actually come from careful planning and using data to find the absolute sweet spot for your operation.
So how do you actually do that? Well, it's a systematic process called design of experiments. So instead of just guessing, engineers identify the key variables, things like cutting speed or the electric current. Then they run these really carefully structured tests, analyze the results with powerful statistical tools like ANOVA, which basically helps separate what's important from what's just noise, and then, boom, they can pinpoint the exact settings that give them the best possible MRR.
And hey, this isn't just theory. This is happening in labs right now. This slide shows how researchers are getting incredible results with these methods. Take Radhakrishnan and Kesavalu. They used a method called Taguchi to find out that pulse duration and peak current were the absolute game changers for their process. Or look at Durai Kumaran's work. They managed to optimize not just for speed, but for tool wear and sustainability all at the same time. That is the real power of data, finding that perfect recipe that balances all these competing needs.
But look, a smart strategy is only half the battle. You also need to bring in the big guns, the seriously impressive technology. And this is where we get into the cool physics of how to cut material faster than ever before.
This slide just brilliantly illustrates the giant leap forward we've made with high-speed machining, or HSM. See, in conventional machining, you've got these high cutting forces, and all the heat you generate just soaks right into the tool and the part. But with HSM, you go so incredibly fast that something amazing happens. The heat literally doesn't have time to transfer. It gets carried away with the little metal chip you're cutting. And what does that mean? Lower forces, less heat stress, and a dramatically higher MRR. It's a game changer.
But high-speed machining is just one tool in this advanced toolbox. You've also got ultrasonic machining, where the tool vibrates at this mind-boggling frequency to basically shake the material loose. Or even thermal-assisted machining, which uses a laser to soften up super tough alloys right before the tool hits them. Each of these techniques is a specialized solution for a really unique manufacturing challenge.
And the impact is just massive. I mean, for a notoriously tough material to cut like Inconel 718, a 2025 study found that just preheating it can reduce the energy you need to cut it by up to 30%. 30%! That is a huge gain in efficiency, all from just changing the physics of the cut. So you've got a smart plan and you've got an advanced technique. But none of it works without the third piece of the puzzle, the physical cutting tool itself. This is where material science really shines.
Modern cutting tools are basically technological marvels, and it's mostly thanks to their coatings. We're talking about these ultra-thin layers of incredibly hard materials that are applied through processes like physical or chemical vapor deposition. You're essentially painting the tool on a molecular level. This coating acts like a suit of armor, resisting heat, cutting down friction, and stopping wear and tear. The better that armor, the harder you can push the tool before it gives up.
And scientists are constantly making these tools tougher. For instance, research by Singh Mali's team created this special hard-face tool with a unique weld overlay, and they achieved a hardness of 309 on the Vickers scale. Now, to put that in perspective, that is way harder than standard tool steels. That kind of real, tangible improvement means you get a tool that lasts longer and can handle a much higher MRR. And it's not just about the coatings. We're also seeing advanced materials like polycrystalline diamond for cutting really tough composites, and totally new ways of cooling.
Instead of just flooding a part with coolant, engineers are using cryogenic cooling with liquid nitrogen, or something called minimum quantity lubrication, which is this super targeted mist. All these methods work together with the tool materials to manage that intense heat and keep the cutting edge razor sharp.
Okay, so we've looked at planning, we've looked at advanced physics, and we've looked at these cutting-edge tools. But the real breakthrough, the key to truly optimizing manufacturing, isn't found in just one of these areas alone.
It's found when you put them all together. It's that simple. The ultimate material removal rate is achieved when you have a data-driven strategy. You pair it with the right advanced machining technique, and you execute it with a tool that is perfectly designed and coded for that exact job. Each piece just makes the others that much better.
So what this really means is that the future of manufacturing isn't just about faster machines or harder tools. It's all about integration. It's about building this holistic system where the planning, the physics, and the material science all work in perfect harmony to just push the boundaries of what we thought was possible.
And that leaves us with a really fascinating question to think about. As the things we build get more complex and the materials we use become even more exotic and difficult to machine, this fusion of disciplines is going to have to evolve even further. So what will that next big breakthrough look like? Well, that's the race we're all watching.